G'day, space fans. Today, this is part 2 in the series on space combat maneuvers, or SCM, considering GEO. In the first video, we showed just some linear drift and just burning in track and what that could do, and a little bit on radial burns. Today, we're going to kind of formalize that into what's called a VBar hop and RBAR hop, natural motion circumnavigation, and the linear drift, and different options for linear drift. Just wanted to also show you guys something cool I received this week from SpaceX. If you guys can see that, it's going to be pretty fun making marshmallows and s'mores with this bad boy. So pretty cool little design here from SpaceX. You can see on the injector face there, it releases the gas around the main outlet there, which makes it easy to ignite. And then the main flow goes down the center. So this thing lights first go every time. It's pretty cool. Yeah, it's a bit of fun. Anyway, let's jump into it. So VBar and RBAR hops. So the first one we're going to look at is a VBar hop, and V stands for velocity because you're burning in the in-track prograde or retrograde direction with your velocity vector. As you can see here, what happens is when we burn in-track, we increase our semi-major axis, in this case by 78 kilometers, and we create this westward drift of 1 degree per day. When we reach the other end, we can take the energy out of the orbit and recircularize and perch ourselves over here. So if we perform a second burn of 2.84 meters per second here at our arrival, 1 orbit period later, we will perch ourselves here. So we would have effectively moved 1 degree, and now we've perched ourselves at our new position. So this is kind of a neat way just to move small amounts in one kind of hop. The downside of it is it takes a full orbit period to do 1 hop. So in this case, because we're at GEO, our orbit period is 24 hours. The advantage is it's very fuel efficient. You can see 2.84 meters per second here. So times 2, 5.86 meters or 5.68 meters per second total in order to perform that maneuver. Another way we can raise our semi-major axis is by burning in the radial direction. So here, what we call the RBAR hop. So radial being the vector between the center of the Earth and the satellite. We're burning positive radial, so we're raising our semi-major axis up by that 78 kilometers. And then after half an orbit period, we shift it back down. So that gives us the same result. We drift 1 degree to the west, but this time we achieve it in only 12 hours. But because we have to burn a lot more delta V to achieve this. And the reason for that is our horizontal velocity is 7 kilometers a second in LEO, about 3 kilometers per second in GEO. Our radial velocity is very small. So we have to burn a lot in the radial direction in order to change our velocity vector by any meaningful amount, because our horizontal velocity or in the in-track direction, is so high, kind of like a right-angled triangle. So here we have to burn 22 meters per second more in delta V in order to perform this. 13.8 meters per second here, and then 13.8 meters per second here. But same result, we've moved ourselves 1 degree to the west. If we didn't cancel that orbit out, what we would have done is just formed what's called an NMC, natural motion circumnavigation. Basically, we would form a football shape here, and we would re-intersect our previous point at perigee every orbit period. But being able to cancel that out here, we've created the same movement where we've drifted by 1 degree. It just cost us more delta V to do so, but we got there in half the time. So these NMCs, you can see I've plotted this out for you now, a full orbit period. So here we're burning negative radial 2 meters per second. This is at GEO. And as you can see here, every orbit period, we now form this nice circumnavigation around a target satellite, which can reside in the middle. So we can be inspecting that satellite. Note, they can also inspect us because from their perspective, we're going around them. So this is useful for doing inspections, but also not having to continuously expel propellant to do so. You just burn once and you're in this NMC forever. So that's kind of neat. There's also what they call FMC, forced motion circumnavigation, and I'll take you through that in the third video. Now I want to consider linear drift. So here in the first video, we created a drift where we drifted at 1 degree per day in a circular orbit, but above GEO. So we were just constantly drifting in a linear fashion. So there's a number of different ways we can get into these linear drifts. The cheapest and easiest is just to perform that Hohmann transfer that I showed you in the first video. So here we burn once in the in-track direction, and this is the M1 satellite here. So we burn at 2.48 meters per second in-track, then orbital mechanics takes over, and when we get to our apogee, we burn 1.42 meters per second, so half the amount initially, and then half the amount at apogee. Total of 2.48 meters per second. And that will recircularize our orbit at a drift of 1 degree west per day. It takes us 12 hours to perform that to get into the drift. And after 2.5 hours, I kind of tracked how far to the east are we. So here, after 2.5 hours, we're about here, right? So we're actually 9 kilometers to the east of our position. So sometimes you might want to get into this drift as fast as possible, or you might want to get to the west as fast as possible, right? So there's ways we can do that. Maneuver type 4, this blue one here. So I'm calling this Hohmann slide cancel. It's kind of like in Modern Warfare where you cancel your slide halfway through it. So we can actually bump up our in-track delta V initially. So here we're doing 2.84 instead of 1.42, so double the in-track velocity. But then we're forcing our semi-major axis back down with a radial burn and canceling it out early. So instead, if we left this to its own devices, it would have drifted on this pattern and would have taken the same 12 hours to get to here, and we'll be drifting at like 2 degrees west per day. But we only want to drift at 1 degree west per day, so we artificially cancel that with a negative radial burn of 5.68, and that puts us into the drift as well. The next type I'm calling radial fast. So here we don't even want to burn in track, because when we do, it moves us away to the east, right? You can see here, both of these, after 2.5 hours, are actually to the east of our position. If we want to go west as fast as possible, there's ways we can do that. So if we just burn radially straight away, we go onto this red track here. So here we're doing an 11.36. Remember, it costs a lot more delta V to burn radially. And then after 2 hours only, we cancel out that delta V, and we add an in-track of 2.84. So that in-track of 2.84 would shift us along the geobelt, and the radial maneuver is just getting us up there, moving our semi-major axis up there. We don't have to cancel out as much in the second burn because we're actually descending and falling towards the Earth. So the Earth has pulled on our orbit and done some of that work for us already. So it only requires 10 on the second burn. And then finally, radial with retrograde boost. So here, if we burn negative in-track, just like we burned here, positive in-track, you can see we move to the east. If we burn negative in-track, we'll move to the west initially. So we can take advantage of that in order to get into our westward position more quickly. You can see here after 2 hours, the radial fast, we were negative 56 kilometers. We were down here to the west. So we got there much quicker. In only 2 hours, we were negative 56 degrees to the west. This guy, we're even more to the west, negative 82 kilometers, to the west. So here we're combining a negative in-track burn to take advantage of that initial movement in the westerly direction, and then applying our radial boost to increase our semi-major axis. And then here after 2.5 hours, we're canceling that out. Okay, now I'm going to show you these in Space Cockpit, and I'll put the link to rebuild this scenario in the chat link below. But what you can see here is I've created a satellite and I've applied a number of different maneuver scenarios to it. So here we can see all of those play out. I'm just going to play it through for you so you can see how they all evolve first of all. So you can see the original object and all of the post-maneuver objects. And they all end up in this 1 degree westward drift pattern. Okay, but they all got there at different times. So if we go back now, jump back half orbit periods at a time, we can start to see these in a little bit more detail. Here's the 2 radial burns. So the one that's even more west, M2 here, it performed the retrograde in-track burn to take advantage of that initial westward movement. This guy's pure radial, M3. Then we perform the second maneuver to circularize our orbit and enter that drift. Over here, we have the 2 in-track burns. So your normal just positive in-track burn here, which takes you on this almost like golden mean. But we move to the east initially and then up. And then this guy where we, M4, where we burnt double the delta V in the in-track direction. So you can see if we left this to its own devices, it would have continued up here. And then would have been double the semi-major axis because it was 2.84 meters per second instead of 1.42. But then we artificially cancelled that motion by dragging the semi-major axis down using the negative radial burn. And then we just have the Hohmann transfer here going along. So you can see there's 4 different ways here that we can get into that linear drift that all cost us different amounts of delta V, but get us there more quickly if we need that, if time is of the essence. Okay, the last thing I wanted to quickly take you through is a couple of cheat codes here. The first one is shown on the left, is called the Oberth effect. So it is most efficient to burn in the in-track direction, so add energy to your orbit when you're traveling as fast as possible. Obviously, that's going to be at perigee, because when you're at apogee, you're traveling slowest, and then you fall all the way down into Earth's gravitational well, converting all of that potential gravitational energy into kinetic energy. And when you hit that perigee point, you're traveling fastest. So if you ignite your thrusters at that point in time, you're going to be getting the best bang for buck for your delta V. The reason for that is it's called the Oberth effect, but when you think about it, your total velocity is going to be a baseline velocity plus whatever velocity your in chemical or ion thrusters are imparting onto your spacecraft. So, once you ignite those engines, the combustion chamber is accelerating the exhaust gases through the throat of the nozzle, and then basically the momentum that you're imparting on the spacecraft is a factor of the exit velocity of that exhaust and the mass of the propellants coming out the back, kind of multiplied together. So your total velocity is going to be that baseline velocity plus whatever that exhaust velocity is. So if you can raise that baseline velocity as much as possible, then your total velocity is going to be higher. So that's essentially what the Oberth effect is. So to take advantage of this, what you might see is when people are performing GTOs or geotransfer orbits, they'll actually go from low Earth orbit up to geostationary orbit in a number of orbit periods. So they'll burn once at perigee, increase the eccentricity of their orbit, come around again. When they hit the next perigee point, they'll burn again, raise their apogee a bit higher. And they'll actually do it over 2 or 3 or 4 stages to get all the way out to GEO. And that's much more fuel efficient to do it that way. The second cheat code shown on the right here is for when we want to do plane changes. So also known as burning cross-track or out of plane. So here, for example, we're in a highly elliptical and highly inclined orbit, and we might want to change or lower our inclination. So we have to burn cross-track to do that. It's most efficient to do that when we're traveling slowest. To visualize this in your head, keep in mind we're traveling in the in-track direction at LEO at like 7 kilometers per second. And we're going to burn like 25 to 50 meters per second cross-track, depending on our thrusters. So that's going to be a tiny little cross-track component vector and a huge in-track component vector. So the resultant vector of that is going to be very stretched out like this. So if you can reduce that in-track vector as much as possible, that in-track component, then relatively speaking, your radial component is going to be affecting the total velocity more. So you want to be reducing that in-track velocity component, and that happens when we're at apogee. So burning cross-track either at perigee or apogee, somewhere on the line of nodes, but so that we're, that's the place to do it. But we want to do it at apogee because that's where we're traveling slowest. So much so that sometimes it's useful to take advantage of the bi-elliptic transfer if we have to do a big plane change. So the bi-elliptic transfer, it's actually cheaper in delta V if you're changing your orbit by a lot. Typically, we use a Hohmann transfer to go from one circular orbit to another. But if you're going from one circular orbit to a really greater circular orbit, that's, I think, 11.9 times bigger than your first orbit, it's actually more efficient to burn above that second orbit and then perform a second burn in what's called a bielliptic transfer. This also applies for plane changes. So sometimes it's more efficient to burn up to a higher apogee first, and then when you reach that higher apogee, do your plane change there, and then come back down. So we do use these bielliptic transfers for saving delta V that way. There's a bunch of other cheat codes as well that I'll kind of drop in through other videos. But that's all I got for you today. Hope you found it helpful, and happy hunting.